So first of all, we start talking about features, which is what we did during the last class, right? They are individual measurable properties or characteristics of the data that you are using to make predictions, right? Let me just quickly go this way. So this is an example of what we have. Now, notice if I'm trying to predict the price of a house in a neighborhood, right? I have the square feet, I have the number of bedrooms, I have the year the house was built, and I'm trying to find out the price, right? So in trying to do this, right, I might not have all of this information every time, but I might want to build a model. Remember the straight line that you created? That's what I'm trying to create with this. But notice that in this particular case, instead of just having two variables, I could have 1,000 variables, right? That's how we move from your simple straight line equation to machine learning, because in machine learning, now you're dealing with so many variables, right? So those variables, right, which is what you have here, for example, your square feet, your number of rooms, your year built. And I was asking you guys the last time, tell me of any other characteristics of a house, and you are giving me different characteristics. Now, we don't know whether the color of a house could affect the price of the house, right? Whether it's a corner lot, yes or no, whether it's going to affect all of those things, you're going to have all of them. And all of them are what we call features in machine learning, right? Remember, I talked about feature engineering. Feature engineering will be the process of you deciding which features you're going to use in that model, because some features might not really have a major impact on the model, right? So this is an example of what we have here. So for example, for features here, square feet, number of rooms, the year built, all of those things are features. And the target price, which is this price, what that particular thing you're going to be predicting after you build your model is what you refer to as your target price, you refer to as your label. No, so in supervised learning, right, whenever you have anything, say a picture, you have to give it a label. A label is literally, um, so if I give the picture of a dog, right, I need to be able to write out that this is a dog. So, um, that name that I give to it, right, is what you refer to as the label. So if I put the picture of a dog, the label will be dog. I put the picture of a cat, the label will be cat. I put the picture of a horse, the label will be horse. That's how it works in machine learning. So your goal in machine learning is to be able to determine what the features are, and then determine the label, and then map the features to the label. Use the features to predict the label. So in doing that, when you want to build your model, you need to know what all of those labels are and what all of those features are, and then you run. In machine learning, we call it to train. You train your machine learning using an algorithm, and then it will give you the model. The model is literally like that straight line to which you can now, when I don't have the price of a particular house, let's say this model, right, which is my training data, only has 300, 250, 400. What if I want to predict for a house that is 5,000 square feet? It wasn't used as part of what I was using to do this, but I should be able to reasonably predict how much it will cost, even though I don't have the price. If I have all of this information, I can use the model to predict what the price will be. That's the idea of machine learning, right? So, and then I did talk about different kinds of data that we talked about. Numerical data, which is like your age, salary, temperature. These are just continuous data, right? And then you have categorical data where you put things in categories: red, blue, green, and all of that, country, gender, all of these things are in different categories. And then we talked about ordinal data, which is data that is used to demonstrate things that are in step by step in increasing progression, e.g., high school bachelor's, master's, PhD. And then we talked about binary data. And then we talked about other kinds of multimodal data like text data, image data, time series, sensor data. All of these are all special types of data. And those are the kind of data. And I mentioned that it's really very important for you to have data to be able to build your models, right? We talked about all of that. And I talked about how feature engineering is the art and science of creating the best features for your model. Like I mentioned, like given the house we are talking about in predicting the prices of houses, there are certain features that might not really affect the price of a house. We need to be able to figure out what can affect the price of a house and what cannot affect the price of a house, right? And just focus on the things that can actually affect the price of a house. And there's a method to that madness, the way it's done. And everything I described to you here is literally like data science. That's what data scientists do. And then after you've worked on all of that data, you now apply artificial intelligence to it, and that's how you get your results. So part of feature engineering is to select the important features, is to transform some of those features, right, to encode. So for example, I talked about yes and no. You can change it to 0 and 1. That's what encoding means. And then you can create new features. Sometimes you actually might combine 2 or more features to create a third feature. So essentially, we're saying that well-crafted features is what will give you better model performance, right? The better, the better your features, your selection of features, the better the model you are going to be creating. So I already talked about all of this. I gave us examples, same thing. So I'm just going to jump and then we'll keep going. So, so just look at this data set, for example, right? Because remember what we did, y is equals to mx plus c. M, right, is your slope. If you remember in the equation that we had, m is your slope. Now, and it's because we had only 2 variables, right? Your y, which is, now in that case, your y is your label because that's what you're trying to predict. Make sense? And then you now have mx, right? The slope of x is your m. But we had 2 variables. What if we had 1,000 variables, right? Then we would have something like m1x plus m2 x2 plus m3x3 plus, you just keep going that way because each of the variables should have its own slope, right? Now look at this, because that's exactly what's going on here. Let's say that your y is the predicted price. You're trying to predict y, which will be equals to, remember the mx in your straight line equation, that will be your w1. And then this is your first variable. This is like your x, which is your square foot, right? Plus, this is your second m. Again, let me go back so that you see what I'm talking about. Remember this equation? Yeah. So now what you have is like m1x1 plus m2x2 plus m3x3. It will just keep going. If it's 1,000 variables, you do the same thing. m1x1 plus m2x2 plus m3x3 plus m4x4 plus m5x5. You continue till the end and you now include your plus c. That's what's happening here. You see what's happening here? So because we have square foots here, we have bedroom here, and we have year built, and we're looking for price. Our price here is literally like your y, what do you call it? Y, let me just use y hash. I can't remember what you call it again. The y with y theta, right? And then we have your w1. Your w1 is literally like your m1 that I mentioned, square feet plus the slope, bedroom plus year built, which are the 3 variables we have here. If we had a 4th variable, we would have had w4, and whatever is there would be something we multiply. Then finally, remember your y is equals to mx plus c. This is b in this place. in machine learning, it's called a bias. So that's why I put it here. Bias is still the same thing like your intercept. If you remember the intercept, which is your C, right? In your regular math, your regular high school math. So if you look at this, you would see that this is exactly the same equation that you had in high school. The only thing is now we are adding more features. So instead of just having two variables, now you can have 1,000 variables, but your intercept, right, is still the same thing. And in this case, your intercept is now referred to as your bias. Right?
And
Yeah.
Dr. Noble, the W1, W3, that's weighted, just like grades are weighted. They're not all equal.
So yeah, and essentially it's just like that slope. Remember the slope? That's exactly what it is, like the slope in your straight line equation. So what's happening? So think of yourself, right? That like you are in a party and you are the jockey that plays the music, right? To get the sound of the music you really want, you have to tweak some of those knobs to actually get the sound that you want. So to your point, right, those W's, right, you have to tweak them. And that's how, and I'm going to show us step by step how you actually do the tweaking, right? So, and notice one of the things that I said here, this is predicted price. Because now this is your model. Remember, this is your model. It's not the actual price, but this is your predicted price. So the point is, if I change my W1, W2, and W3, it would affect your Y. These ones are going to be constant. The only thing that is changing is W1, W2, W3, and W4. So essentially what I'm doing, right, and I will show you, let me not jump. So this is the point, right? It's almost something like this, right? We're going to be tweaking each of these. The knob, we move it up and down or move it up until we are able to get the exact pricing. And I'll show you what that means. So think of this, right? This is your weighted sum and this is your prediction error. But let me just show you an example. Same thing I was talking about here, like a jockey. You have to keep turning those knobs until you get the exact sound you want. That's what happens in machine learning. Right? So let's go. Let me talk about bias first, and then later we'll come back to errors, because the prediction error is what will help you decide how to tweak your W's, W1, W2, and W3. Now, I want you to understand all of this. You are not going to do the math, but I want you to understand what's happening when the computer does the math for you. You are not going to do all of this math, right? You just need to understand what's going on in the computer when you're doing your stuff. Make sense? So in machine learning, especially in linear models and neural networks, right? So your y is equals to mx plus c. That thing you have there, the equation of a straight line, is essentially a linear model, right? But there's also something called neural networks, which is what we use in deep learning, right? He said in both of those cases, in machine learning, especially in linear models and neural networks, bias is a learnable parameter. What do we mean by learnable parameter? So you're going to keep hearing the word learnable parameter. In other words, right, it can change, it's tweakable, right? Is a learnable parameter added to the weighted sum of inputs before applying an activation function. And I'm going to explain what all of that is. If you just go with me, gradually I will show you. So notice that I talked about W1, X1, which is what we did, right? Remember your X1 was like the number of rooms and all of that. So it's the same formula that we have here. And then your B is your bias. Remember? So in in uh, in your linear models, like what we had, like what we did, right, previously, this is okay. This is what happens. But then as we begin to move into machine learning, right, all of a sudden, there is an additional thing that we are going to add there, because if you come into machine learning, right, some of the models are not going to be a straight line, right? Some of the models are going to be something like they are going to be curved, or they are going to go something like this, right? When you create the model, it will go something like this and this. So it might not always be a straight line. So how do you account for that, right? You account for that by introducing something we call an activation function. And I'm going to show you how an activation function works. In other words, notice your y, your actual y will be, you would apply an activation function to everything you get here to get your actual y, right? In other words, that will be y hash will be equals to activation of z. That's what will give you all of this. So that's why I have this here. So if you see, we are building up the information one step on the other. So bias allows the model to shift the activation function left or right. Without it, the model is restricted to functions that always pass through the origin, right? Let me go back to what you know again to try to explain what this means. Remember this straight line, right? Without the activation function, this straight line is always going to be going through zero. It's always going to be going through zero. But when you apply an activation function, it allows the line go through any point on y. That's what an activation function does. But just hold that thought, right? Because as we keep going into it, we're always going to keep bumping into activation functions, so that even if you don't understand it immediately now, as we keep going over and over again, you're going to get the gist of activation function later. But just hold that in your thoughts, that an activation function helps you move this loop up and down anywhere you want to move it to mathematically. Okay, so let me go back there. So bias, which is your intercept, right? Your intercept, that's C, which in machine learning I said is called bias. Your intercept, which is the same thing as your, allows the model to shift the activation function left or right. Without it, the model is restricted to functions that always pass through the 0, 0, which is extremely limiting. So let's go. So for a simple linear regression, right? The formula for a simple linear regression is y is equals to w times x plus b. Remember, this is what we started with, the equation of a straight line. So it's just telling you for a very simple regression, that's just what it is, right? Where x is the input feature. Remember, we talked about the features. There are different features. So that's the feature. I'm just repeating the same thing I said before. W is the weight, also called the slope or coefficient. And then your B is the bias. And then Y is your predicted value. So you already know this. I'm not adding anything else. So same thing here, right? So I'm just reiterating it for knowledge sake. The weight controls the slope, right? So it's like the slope in the straight line equation. The bias controls the intercept. That's where the line crosses the y-axis. That's what your bias is. Now notice, without bias, right, all lines are forced to go through the origin, which is rarely ideal. So sometimes you notice, depending on where your dots are, you don't always have to go through the straight line, but the bias or the intercept is what helps you go through any point where it best fits on your y-axis. Okay, so that's what now brings us to neural networks, right? Because what I just described right now is what's happening in each neuron. But notice in this place, there are so many neurons. I just described what happens in one neuron. Everything I described to you is what happens in one neuron. But what if I create this mathematical system now called a neural network? So the idea of the neural network literally came from the brain when we do biomimicry. So when people were trying to design planes, right, they kept studying the bird. How did the bird fly? And that's how they began to look at the bird and study to learn how to build planes, right? When they built submarines, they looked at fishes to see how fishes behaved, and that gave them ideas of how to build submarines and all kinds of things. There are all kinds of things that we have built today as humans, right? And we build it by looking at the human equivalent of it, right? And that's something we call biomimicry. So now all of a sudden we are trying to build this thing that has artificial intelligence. And we know intelligence comes from the brain. So they began to look at the brain, neurons in the brain. How do they work? How do they function? And that's how they came up with these ideas. Now, when they came up with these ideas, they had to try to reduce this to some kind of mathematics, right? So that what they have created would also behave kind of like a brain so that it will give us intelligence. Make sense? So that's how we came about neural networks, right? So, and the idea is, so you see this point, the idea is if I put in some information about my features here, because these are what we call your input layer, the layers here at this extreme end are referred to as your input layers. The layers here are referred to as your output layers. So a bunch of each of this is called a neuron. So this, if you have a bunch of neurons, right, vertically like this, they are referred to as a layer. And this is another layer, this is another layer, this is another layer, this is another layer. But broadly, we refer to them as three types of layer. You have your input layer, your output layer, and every other thing that is inside, right? Because you can have 1,000 of these. Everything that is in between the input and the output layer, we refer to them as the hidden layer. Does that make sense? Questions? Any questions? So the idea is when I get, for example, a picture, right, of a dog or a cat, and I'm trying to predict what it is, right? I extract information, I convert that picture to numbers, raw numbers, right? And I do some math on it. And the math I do on each of these neurons is the math that I showed you, because it's all pure algebra, it's not complicated math, right? And for each of them, right, they will do the same math that I showed you, which was a very simple math if you understand a bit of that math, right? So that's what's going to be happening in each of these. And then when it does some work here, it will transfer that information to this other bunch of layers. And you can see how all of these lines connect with each of them, right? So that's what begins to make it complicated, not because it's hard, but because there are so many operations that are going on at the same time, which could be in thousands or in millions of operations, little math. Because for each of those, right, it's going to be calculating what is my y is equals to x1 plus x2, w1 x1 plus w2 x2 plus w3 x3 plus then plus b. It will do that for each of these. And look at, for example, this neuron alone, this line is going this way. This will talk to this, 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 talk to this. So it's like it's talking to all the neurons, transferring information from these neurons to this bunch of 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 neurons. So dozens and millions and millions of calculations. So each time you go to ChatGPT, for example, and you type in something, millions of calculations happen to immediately give you the result you're getting. But guess what? They happen very fast. And that's what computers do. If we gave you the math to do, it will take you a long time, but computers will just spit out that thing in microseconds. So that's exactly what's happening. And this is what we refer to as neural networks, right? So And I'm going to we're going to have you, I'm going to include a couple of videos that you can watch that can actually help you begin to appreciate and understand what's going on here. So in neural networks, in each neuron, this is what's happening, right? So you have your W1X1 plus B, right? And summation, what summation means? Summation is essentially W1 X1 plus W2 X2 plus W3. So if it's like 1,000 of them, I will be equals to 1 to 1,000. So what this is just doing is adding W1 X1 plus W2 X2 plus W3 X3 plus blah, 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 to 1,000. All of that, we are just saying we are summing it up, where our I is from 1 to 1,000 or whatever. So that's what's happening here. So bias acts like a tuner knob. Remember, I was talking about tuner knob. That's what bias does. Allows each neuron to activate at the right time. Now, your brain, right? Notice that all the neurons in your brain are not firing at the same time. If they fire at the same time, you are going to go crazy, right? So only some parts of your brain are activating at any one time. What helps these particular neurons know which of them should be firing and which of them should not be firing at one time? That's why it says bias, which is your intercept, acts like a tuner knob. It allows each neuron to activate at the right time. It helps them activate it gives the model more flexibility to fit patterns in the data, and you're going to see some of those. So just like weights, right? We talked about weights, which is like your slope. Biases are initialized initially at the start of the training. What does that mean? So I showed you, for example, that equation, right? Y is equals to W1X1, W2X2, blah, blah, blah. When you start your calculations, right, notice the only thing you have are the features, right? Like, you know, the number of rooms, you know, all the other information about the features. But guess what? You don't know what your W1 is. You don't know what your W2 is. Those are things you have to figure out. So do you know how you do that? You just assign it any number. That's how you start, right? When you assign it any number, it will now give you some predicted Y. So you now, you know the actual Y, because remember in your label, right, you already put the actual Y, but your equation predicts another Y for you. So to know whether your new Y is accurate, you would have to say your actual, your predicted Y minus your actual Y, right? That's what will give you the error. Because ideally, if your model predicts it accurately, right, your actual minus your predicted will be equals to what? 0, correct. But if it doesn't equal to 0, then it gives you a particular value. That means you have to go tweak your W a little bit. You keep tweaking your W until your Y hat minus your actual Y will be equals to 0. That's everything I described to you right now is what machine learning is. But it's not just doing it in one neuron, it's doing it in 1,000 neurons at the same time. Does that make sense? Yeah. So it's a beautiful thing, and you can see how I'm excited about, like, I'm trying to figure out how to communicate it so that, like, it's very easy, but you can see it's also like I can communicate it easily, but you also enjoy it based on what you already know. You don't have to get some grand math to understand it. So, but before we actually begin to do the things, I want you to have some kind of idea what's going on so that when we start doing it, you're not totally lost in what we're doing. So now, just like weights, biases are initialized. So initialize means you just assign them any random value, right? And then you run it, you get your Y, then you minus your predicted from your actual, you get something. And if it doesn't, it's too, if there is an error that is high, you try to tweak with your W and you keep doing that. Now, the training process which we call gradient descent, right, learns the optimal bias values that helps minimize the error. So there's something called gradient descent, right? That's when you actually go into differential equation, right? It helps you determine the best value of bias. So that, you know, getting the right weight and the right biases is something that would be that will be figured out mathematically, right? And we use something called gradient descent. That's why I said I would now include the videos for gradient descent so that you can watch it and see what it means, and then all of that, you know, so you can figure out what's going on. So think of this, right? Effect of bias on a linear function. Let's say we have an equation y is equals to wx plus b. That's what we have, right? Y is equals to wx plus b. So notice here, you see the red one. Notice this is your y axis. This is your 0 to this point, 0 to this point. So this is your 0, 0 point here, right? So for your y will be equals to 2x plus minus 4. Why is it minus 4 here? Because the intercept is minus 4. You can notice all of the lines are the same thing, but the difference in the lines is their intercept. Notice where this is minus 4. Your intercept, what is your intercept? Your intercept is the point where your line crosses the y-axis, right? So for here, this is minus 4, right? For the green line, where does it cross it? It crosses it at 0. That's why you have this as 0. And then for the blue line, where does it cross? Because this is your, sorry, this is your 0, 0 line here. I mistakenly said it was here. This is your 0, 0 line because this is 0, x, y. So this is your 0, 0 line. So here is your 4 because this is where this line crosses the y-axis. Any questions? Please make sure you're asking questions if you don't understand anything. I don't want you to.
No, I just furiously Googled what it was and I figured it out. So
okay, good. So everything here is what I just described. All three lines have the same slope. So notice that all of these three lines have the same slope and their slope is 2. And you remember how we got this slope? How did we know that this is 2? All we need to do, if this is a straight line, to get the slope of this line, we'll say this divided by this, right? Delta y divided by delta x, right? Which is 4, 0 to 4, right? Minus 0 to 2. If you divide it, you will get 2. Same thing here. If you do this, you would also get 2. So each of them has a slope of 2. That's why we have this 2, 2, 2, because our W is now 2, 2, 2, 2 for each of them. But the intercepts are different, right? The intercept is where your line crosses the y-axis. So this one crosses at minus 4, this crosses at 0, and this crosses at 3. That's why you have minus 4, 0, and 3. So all three lines have the same slope, right? Their weight is
real quick. Can you go back
oh,
to that last slide? I'm sorry.
Sure. So this is your x, and this is your y-axis. So this is your 0, 0 point here. So the red line has a bias of 4, so it crosses the y-axis lower. The green line has a passes through the origin, which is the 0, 0 line, and then the blue line has a bias of 3, so it shifts the whole function upwards. So that's what bias does. They might have the same slope, but they will shift away from the y-axis, each of them. So it says bias allows your model to start from the right place. That's what bias does for you, right? It is crucial when data doesn't align perfectly with the origin. So if the data doesn't align perfectly with the origin, what do? You move the model to the point, right? So that's why bias is important. It gives the model freedom to fit real world patterns more accurately, right? So in linear regression, right, the question is, are bias and intercept really the same thing in linear regression? In simple terms, they are the same thing. So in linear regression, the bias and intercept refer to the same thing, which is what I was talking about. So, but in neural networks, right? In machine learning, especially neural networks, each neuron, I already told us, remember when I told us that it's the same equation for each of those neurons that I showed you in the neural network, right? Each of them, this is the equation of what's going on there. Here it says, here, bias is not just a regression intercept. It allows every neuron to shift its activation, right? It's bias and intercept are essentially the same thing, but it says for neural networks, right? When we're talking of each of those neurons, here bias is not just a regression intercept. It allows each neuron, each of those neurons, remember the cycles, to shift its activation just like an intercept shifts a line. So while in the straight line is just shifting the line, in this particular place is shifting its activation. What does it mean to shift an activation? Remember I told you that you have so many neurons in your brain, not all of them are firing at the same time. If all of them are firing at the same time, you are going to be psycho. You know, like you have a mental situation because your brain is moving too fast because everything is running. So what happens is some parts of your brain are quiet and others, depending on what you need to do or what you're doing. So if you are in love, certain parts of your, you know, you're with someone that you love, certain parts of your brain will be going off. If you're mad, certain parts of your brain. So everything is not happening at the same time. So what helps control each of those neurons is what we call the activation function. So just like the straight line, you're using intercept to move the line. That's the same way in neural networks, you're using activation function. It helps, the bias helps shift the activation function. Tell it when it will fire. And then we'll still get to know some more of this. So let me read it again. Here, bias is not just a regression intercept. It allows every neuron to activate, to shift its activation, just like an intercept shifts a line. But in deep learning, you can't really call it an intercept anymore because you are no longer fitting a straight line, you are shaping a complex function, right? Because in straight lines, like if you're doing your regression, which is your XY thing, and we create a straight line, a lot of times it's just a straight line. But when you come into a lot of things that happen in real life, which is what neural networks helps you solve, a lot of those phenomena are not straight lines. Sometimes they are bent, sometimes they are curved, depending on what it is. Sometimes the functions go something like this. What helps it curve it, right? So that it becomes what we call a non-linear function is the activation function. So what we had before is what you call a linear function because it's straight, linear. But when you have things that are curved and they are complex, that's when you refer to it as non-linear functions. Okay, so we'll now go. If you're dealing with linear regression, we can say bias is the same thing as intercept. But if you're dealing with machine learning or deep learning, bias is the same concept, but it is used in every neuron to add flexibility to those neurons. So help them come on and come off. So in summary, bias is an extra parameter added to the weighted sum of inputs. Its purpose is to allow the model to shift predictions and improve flexibility. It represents the model's default output when all inputs are zero. You know, it is trained like other parameters. Yes, it's learned from data. So I mentioned to you, remember the weights, we don't have the weights. We just predict, we just give anything to the weights and figure it out later. That's the same thing your bias is too. So do we have more time? Where are we with time?
You were at 11:34 is end of class, so you got about 13 minutes left.
Okay, I don't know if we can. Okay, let me just introduce us to activation functions. I'll just introduce us to activation functions, but we will come back to it again. So Remember I told you about activation functions, right? It's something you apply. Remember you have your y is equal to mx plus c. Now that's a straight line. Activation function is something that I apply to that line, so that it's no longer straight. That's why we call it a nonlinear function, right? So that it will represent the actual phenomenon that you want it to represent in real life. Because most things in life are not straight lines, right? And there are different kinds of activation function depending on what kind of problem you're trying to solve. You can choose the right activation function to make your linear function non-linear, and that's what we refer to an activation function. So it's a mathematical function applied to the output of the neuron. What's the output of the neuron? Remember, y is equals to mx plus c. Your output is that y, or y hatch on top of it, right? That's your output. So it's applied to the output of the neuron. It introduces non-linearity, which is what I was talking about, into the model, allowing the network to learn and represent complex patterns in the data. Without this linear feature, a neural network would behave like a linear regression model, no matter how many layers it has, right? So to the point I was making, what we had before, like when you draw the equation of a straight line, it just gives you a linear model. But to actually represent a lot of things that happen in real life, it has to be nonlinear. So, which is the point? Activation functions introduce nonlinearity, right? Which enables neural networks to learn complex relationships, right? A straight line will not help you learn complex relationships. So if I'm trying to navigate something complex, right, I need to change those straight lines into, nonlinear lines. Patterns like if this and that, or only when this exceeds a threshold. So if I'm trying to make a decision to be like, if this happens, do this. If this happens, do this. So if I say, if this is a straight line, and I say, if this happens, do this. If this happens, do this, right? That's what nonlinearity is. It's not just going to be continuously straight. What helps those the functions turn into the shape we want it to turn, depending on the complexity of the problem, is what you refer to as your activation functions. They learn decision boundaries that curve or bend, which is what I just described. So non-linearity is one of the most powerful and important ideas in neural networks. So what's non-linearity again? You get that your straight line, and then there is a particular problem that requires you to bend it for it to fit the data and go this way and fit the data. That's what non-linearity is. So non-linearity means that the function does not produce a straight line when graphed, and its output is not a direct proportion of the input. That's what non-linearity is. It might sound, so for example, this here is a straight line, the dot, 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 dot. But then you see, this is an example of a non-linear function. This is an example of a non-linear function. Look at the blue one. The blue one starts here, goes here, and then it goes up. Right? These are all examples of nonlinear functions. But what helps you get a nonlinear function? It's what we refer to as your activation function, and there are different types. So if you look up here, right, you can see the different types of some of the different types of activation functions. The broken line is your linear line, which is your y is equals to x. Once this is this, then this must be equals to this. When this is this, this must be equals to this. But there are certain phenomena in life that don't go straight, and then you have something like this. It starts this way, and later I'm going to show you examples of where real life situations are non-linear, right? But if you understand the concept of non-linearity, it now makes your understanding of machine learning a whole lot easier. So these are different. So this is a typical linear function, but this is another type of linear function. What this is saying is, as far as this thing remains zero, you're going to stay here. So for example, your thermostat in your house, when you turn it on, right? certain times, even though you've turned it to a particular temperature, it's always going to remain the same temperature. But when it hits a particular temperature, then it takes off, right? So that would be something like this, right? So how do you model that mathematically? That particular condition I gave you, if I turned it, right, your house is going to remain normal at a particular temperature. The only time it will all of a sudden turn on the heat is when it gets to a particular temperature, then it takes off. So something like that, you can reasonably model it with this. So these are all different types of activation functions, right? So some of a lot of the things that happens in your brain, for example, would be represented by this. When this happens, do this, or when this happens, do that, or we just go this way or that way, right? So and it's all what I described here, but we will come back to this, but I think we're going to end here. Watch the videos that I'm going to put. I'll try to put them right now. Watch some of those videos. So I'll put something on gradient descent, forward propagation, backward propagation, what do you call it, neural networks. But we've discussed some of those things. So now, if I put them, it will make a little more sense to you because we've discussed them.